Hi everyone, I've been told to just kick off, so kick off I shall. Hi, my name's Richard. I'm a developer evangelist for Here Technologies, and we are the world's leading location technology company, and that means that location matters to me. Here's a fun fact. I submitted this as a full hour talk, and because it got accepted as a 15-minute lightning talk, so I have an interesting challenge ahead of me. I wanted to do a talk about location. Where does location come from? When we use location in our app, we usually have something like this. We have a latitude and a longitude, but we don't necessarily understand really what that means or where it comes from. We use that maybe to start a routing API or to center a map, all these kind of things. But we don't necessarily understand what that means. So I had a wonderful 1-hour talk. There were nice stories about the Cold War and Ronald Reagan and fighter jets and space and dinosaurs and all that kind of thing. For a 15-minute talk, I had to cut that down a little bit, and I picked out kind of one thing from that talk. And that really is the question, where does that location come from? And the answer is usually GPS. Again, that's only partially true, and if we had the full talk, we could talk about that as well. But really what I want you to take away from the next 15 minutes is the idea of how does GPS actually work? Because we use that every day. As developers, often we use location in our apps on our Android phone. That will usually come from GPS. But do we actually know how that works? We have an idea there's satellites in space, and we talk to them, and then we know where we are. But how does that work? And so that's what I'm going to talk about in 15 minutes, kind of try to get the idea across of how does that work? How do we actually get a location from GPS? And then also, if we have a little time left, we can talk a little bit about why is that location always awful? Why is it always, oh your Uber driver is going to be here in 4 minutes. No, actually 15 minutes. No, actually he's already there. So where do these problems come from? And maybe if we understand that, we can deal with that a little bit better in our applications. Okay, so GPS is a system of 24 satellites that orbit the Earth at 20,000 kilometers. And it is a system designed so that at least 4 of those satellites are visible at any given time. Okay, that's nice. So we shoot satellites into space. So how do we determine our position using these satellites? And that's basically just 4 steps. One is we have to find satellites, at least 4 of them, hence the system being designed to show it at a minimum 4 satellites at any given time. Second, we need to find out where they are. Third, we need to find out how far away we are from them. And then we use the magic of trilateration to calculate where we are. And I actually want to start with step 4 with trilateration, because when we understand trilateration, we understand why these other 3 steps are necessary. So, simple example of trilateration. I'm going to do this in 2D because 2D is much more easy to understand than 3D. So let's say I want to know where I am, and I'm calling a friend of mine who lives in Magdeburg, and I'm asking him, hey, do you know where I am? And you can already see this is a very practical real-life example. And he's telling me, I don't know where you are, but I do, for some reason, know that you are 128 kilometers away from me. We've all had those phone calls, right? What that means at that point is still don't know where I am, but I know I must be somewhere on that red circle, because those are the only places in the world that are 128 kilometers away from Magdeburg. Okay, so that helps me somewhat, but not enough. So I call another friend. He lives in Stettin, and I ask him, do you know where I am? And he says, no, but I happen to know you're 127 kilometers away from me. And that actually helps a lot, because now we can only be in 2 spots anymore. The 2 spots where those 2 circles intersect. So I call another friend, he lives in Cottbus, and once again I ask him the question, do you know where I am? And he says, no, but I happen to know you are 107 kilometers away from me. And so I draw another circle, and now, very, very conveniently, there's only 1 spot where those 3 circles intersect, and in that case, I would be in Berlin, which is where I normally live. Now, if you imagine this with an added dimension, and you imagine our friends as being satellites, and you imagine those circles actually being spheres around the satellites, and then you can also see 1 satellite, another satellite, another satellite, another satellite. With the added dimension, we obviously need another satellite. Then those spheres would only intersect in 1 point. So here's the thing, though. There's only 3 satellites on this picture, and you actually only need 3. Any idea why? Come again? Yes, I don't know if I understood it correctly, but the answer is, of course, you get 2 positions based on this, but one of them is out in space. So unless you're an astronaut, like this fella up there, it's probably the one that's on Earth. Or another way to look at it, the Earth is conveniently round. You can just use the Earth as the 4th sphere. We actually do need 4 satellites, but we need them later, and we'll see why. Okay, so we understand trilateration. It's basically just circles and spheres and intersections, and everything is fine. So now we kind of understand, well, we need 4 satellites, so we can do those spheres. We need to figure out where they are so we know where to draw the spheres around. We need to figure out they're in Magdeburg or Cottbus or whatever, or wherever. And we need to figure out how far away they are from us so we know what the diameter of the sphere is. So let's figure out how we can do those 3 things. First, we have to find the 4 satellites, and very conveniently, those satellites permanently send out a signal. So they're saying hello to us all the time. All we need is a receiver that can read and understand that signal, and in our Android phones, very conveniently, that receiver is already provided. So easy, check mark. Also very good when you only have 15 minutes and need to go through it quickly. It's always nice when some of those points are easy to explain. Determine their position. It's a little bit more tricky, but again, fortunately, the satellites, like my friends, actually know where they are. The GPS signal that they're sending out contains a whole bunch of information like date and time, and how well the satellite's feeling, if you should trust it or not. And it contains 2 other things. One is called ephemeris, which is the Greek word for diary, and the other is called almanac, which is basically a yearbook. And the ephemeris data essentially contains the location of where the satellite is. They've got pretty stable orbits, so they generally know where they are anyway, and they're monitored by ground stations, and the ground stations can give them information as well. So the satellite actually knows where it is. The almanac also has information, course location on all of the other satellites, and a bunch of other information, including an ionospheric model, which will become useful later. Here's a really interesting thing about this, though. It takes forever to transmit that data. It's sent at a really slow data rate. To get this whole data takes 12 minutes. And if you have a GPS receiver that's cold, which is it has no idea where it is, it has no information about where satellites are, it literally would take 12 minutes to get a fix in the worst case. Now, the reason why your Android device always gets a quick fix is you can just download that information over the internet. That's called AGPS or AGNSS. So you don't actually need that information from the satellites. You can just download it off the internet if you happen to have an internet connection, which again, conveniently, our Android phones usually have. Okay, very nice. Another check mark, we can determine their position. Now comes the harder part, figuring out how far away they are from us. And we need to do this very, very precisely. Now, satellites, GPS satellites, are really just atomic clocks we've shot into space. So they know what time it is very, very precisely. And they send a signal to us. And so what we could do is we could figure out what time it was when the signal was sent, what time it is when I receive the signal, and then just, signal gets sent at the speed of light, distance is time times speed, blah, blah, blah. We can just figure out how long that signal was traveling, and then we know the distance, because we know how fast it is traveling. Very cool, right? Done? Anyone see the problem? That is correct. Our Android phone, unfortunately, does not have an atomic clock built in, because if it did, it would be much bigger and much more expensive. So this, unfortunately, doesn't work. It's a good idea, though, and there's one thing you might notice. One thing is that all of the signals I'm getting, all of the distances I'm measuring this way to the signals, are all off by the same way. Like my clock on my phone is off, it's not precise, it's not synchronized with the satellites, but the satellites are all very, very precise and therefore synchronized, and that means it is all off by the same amount. That's what's called a pseudo-range. I don't exactly know what the range is, but it's wrong in the same way, which is really convenient, because if I can determine what that offset is, the way in which it is wrong is, I would get the correct distance to all satellites. And this is actually where the fourth satellite comes in, because as it happens when I use 4 satellites, when I pick the right offset, only then do those 4 spheres align in one spot. Now, this ends up being a huge mathematical equation, and in fact, that mathematical equation is so long that it's also not on my 1-hour talk slides. So we'll just skip over this conveniently, not bother with the math too much, and just realize that that actually works. You can solve this with math, and that is why you need 4 satellites, because you can't use the Earth for that. Cool. So we found 4 satellites, we've determined their position, we know how far away they are from us, and now I just do trilateration like we did earlier, and that calculation is actually fairly simple, and I can get a position. Now, if it is so easy, why does my Uber driver still constantly hop around the map and I get a wrong location? Why is this all so imprecise? Well, by its nature, GPS is only accurate to be about 5 meters in the best of conditions. And that usually the best of conditions you don't have. So let's look at what non-ideal conditions are. What are some things that affect GPS? I need to hurry up because I've got less than 5 minutes, but this is really cool. I left this in because GPS is actually affected by relativity theory. Because as it turns out, both by special and by general relativity, because it turns out the satellites move really, really quickly, 14,000 kilometers an hour, and that means they actually move faster than the clocks on the ground, and that means they actually run slower by 7 microseconds every day. And gravity also alters time, and they're further away from the planet, so there's less gravity, so actually run faster by around 45 microseconds a day, which means they're off by, I won't do the math in my head because I forgot what the numbers were, but those couple of microseconds that it ends up running wrong adds up to 11 kilometers a day. So the clocks are actually set to run slower than they're supposed to be to compensate for that. That won't really affect you every day because the clocks are set to compensate that, but it's so cool I just have to talk about it, and your physics teacher will probably really enjoy the fact that you're using relativity theory every day in your life. Another thing that affects it is the ionosphere. There is a charged layer of the atmosphere that actually bends the radio signal, which is also why the satellite has some ionosphere weather reports, so you can compensate for that a little bit. But it's kind of an imprecise science, and so depending on how the weather is in the ionosphere, the signal will be worse or better. Not much you can do about it, except maybe to get a better ionosphere weather report. But the thing that very often really affects you on an everyday basis, particularly when you're calling a cab in Manhattan, are multipath and reflection errors. Turns out that, first, satellites are easily blocked. We all know in a building we don't get GPS, so if there's a satellite I would see in the sky, but there's a building in front of it, I don't see it. And so suddenly I have fewer satellites. And the fewer satellites I have, the more difficult that equation gets to solve, and the less precise it is. And sometimes I might not even see the 4 satellites or more satellites because there's so much obstruction. But it gets worse. If I have a big glass building, the signal might actually bounce off the building. So I get a signal, but it traveled a longer path than I thought it did. And that also means I get a wrong position. And there's a lot to talk about for all of these kind of things, but my time, I think, is about up. So I just hope this was kind of interesting for you. You learned one interesting thing today, which is how GPS, which you use every day, which you probably all used to get here today, how that actually works in principle. And maybe a little bit about the problem, so when you use it in your apps, you have a little bit better understanding of what goes wrong, even if it's not necessarily a solution. And here's a picture of a dinosaur. Thank you very much.